بسم الله الرحمن الرحيم. أعزائي الطلبة السلام عليكم. We came back with the last part of session 7. Here we are going to talk about the wavelet transform and its application in image processing. So what is wavelet transform and how we can use it in image processing? This will be discussed shortly in this lecture. So let's jump to the slides and see what is the wavelet and how we can use it. So this session will be talking about image transformation or the image transform part 3, the discrete wavelet transform. Discrete wavelet transform. We repeat the main idea of the types of the transformation. This we will talk about two-dimensional discrete wavelet transform and its application shortly. Again, as we have seen in the previous lectures in this session, the well-known types of transformations are the classic transforms. This includes Fourier transform, cosine transform, or cosine and sine transforms, and the wavelet transform. This will be the last part in this session. However, you can find again, as we discussed this before, other transforms are other trendy transformations like ridgelet, contourlet, beamlet, etc. And you can have a long list of new transforms that deal with different aspects and different applications. So let's go to the wavelet transform part. As an introductory information, if we go back to the Fourier transform and we say why we need a new transformation once the DFT or the Fourier transform is good enough to apply or to do our work. In fact, the Fourier transform breaks down the signal into constituent sinusoids. So we can use sinusoidal functions to decompose the signal into different frequencies or using sinusoidal shapes. For example, this is the input, and we can see the DFT or the FT in the frequency domain having this spectrum. So now what's the problem with this? What's wrong with the Fourier transform? Why it's not enough sometimes to take on the Fourier transform? Now, the first and the main idea behind this issue is that the Fourier, if you apply Fourier, you lose the time information in your frequency domain, because it's a long range or long time observation transform. When you apply the summation or the integration, you are averaging or finding the long time observation in the time domain to get the frequency content. And this will cause actually to lose the specific or particular frequency to be or the particular event in time, and how this has been reflected in frequency. This is the time. Now, in the Fourier transform, you are going to use the averaging or let's say the long observation operation, and this means that the short changes or the short time changes will be lost and will be combined with other components in the frequency domain. For example, if we have a drift in frequency or maybe trends, abrupt changes, very short time operations that can be done can be obtained in time domain on the spatial domain in case of the images. These events will be lost when we find the Fourier transform as an average or as a spectrum for a long time observation. Moreover, the calculations in the Fourier transform are complex because we are using exponential complex, and this will lead to complex numbers. This is one of the also the disadvantages of the Fourier transform. Let's talk about the stationarity before going to the DWT. Now, the stationarity means, if you remember, that the signal is called stationary if this signal doesn't change with the frequency content doesn't change with time. All the frequencies are existing at all times. This type of signals is called stationary. Now, in the case of non-stationary signals, the frequency changes in time, which means that the signal with frequency content changes with time, and not all frequencies are existing at all times. A good example of this non-stationary type is the chirp signal. Let's have a look on the signal. This is the stationary one. We have the combination of three frequencies, 2 Hz, 10 Hz, and 20 Hz in this image. And this is the spectrum at 2, 10, and 20 Hz in the frequency domain. And this is the magnitude. It looks like that they have 3 peaks or 3 deltas in the positive frequency range. Now, if we have non-stationary signal with 2 Hz being varying between 0 and 0.04, not stationary, but it is changing with time. And for the 10 Hz, the same thing, and the 20 Hz, and we have a different range of drifts in or abrupts in this frequency. Now, if we go to this sort of the signal is shown in the frequency domain. Now, we again have a peak at 2 Hz, we have a peak at 10 Hz, and at 20 Hz. However, you cannot capture this drift in the frequency domain, and this could be a bad or a disadvantage of the Fourier transform. Again, another example. Here we have, as you see here, we have frequency from 2 to 20 Hz. We start with low frequency and go up to high frequency. Here, this is the spectrum. As you see here, we have the spectrum of the signal. Now, if we have the other signal, but in the opposite direction, now we have the frequency is at 20 Hz and it reduces down to 2 Hz. Or maybe two frequencies, 2 and 20. But they are in time, they are in reverse in time. The spectrum again will be the same as in case of the spectrum of the first signal. So you cannot capture using the Fourier transform such changes or abrupts or modifications in the spatial or in time domain. So what to do? What is the solution in this case? So they are different in time domain, but the spectrum is the same in the frequency domain. So what is the next step to apply, or what to do in this case in order to capture these changes or to track such changes in the spatial domain or in time domain? Of course, the Fourier transform cannot solve this problem. What could be a possible solution is to use what we call the short-time Fourier transform. The short-time Fourier transform STFT. Actually, in the 1946, Dennis Geber developed a short-time Fourier transform using the windowing technique. In this case, what we are going to do, we are going to divide the time and frequency into small windows, and let this window move on time, and we can record the frequency content of this window. So we divide the time into short times, or short time windows or intervals, and register the frequency or record the frequency of these small windows, and sketch this in time frequency grid as you see here. Now the good thing that the Wavelet transform can be also a good solution to solve this and other problems as well. Let's start with the wavelet in one dimension. Here it can effectively limit the duration and has it's a small wavelet means a small wave that effectively limits the duration and has an average value of 0. So any shape of waves that can limit the duration with limited duration, and it has an average value of 0. In this case, we depicted the wavelet for Daubechies. Scientist Daubechies, and this is Daubechies wavelet of the type 10, dB10. This is a sine wave. Now, the sine wave is not limited, is not with a limited duration. Here, the average also maybe 0, but it's not with a limited duration. Now, what are the properties that are required to apply Wavelet transform is to have the wavelets having these three conditions. Now, it's a short time localized wave with 0 integral value or with 0 average value. It has the possibility to for time shifting. It can be scaled and shifted in time, and the flexibility it can be used flexibly in different applications. Okay, let's go now to see The equation of the wavelet, actually the continuous wavelet transform, is a little bit difficult because we have here the input signal or the input function that we want to apply the Fourier transform to it. Here we have the base functions, and this is the integration. And once the psi or the base function can be changed, we can define specifically what is psi every time we need to redefine this value. And sometimes this makes the operation a little bit difficult. We'll see next how we can simplify this issue. Now this is the continuous wavelet out for scale A and translation B. Scale means the frequency that we scaled the wavelet into it, and the translation and the shifting in time that has been done. Now having low scale, we get high frequency. Having high scale, we have low frequency. This is a normalization factor, no problem. And this is the mother wavelet that can be used, the wavelet group of wavelets that can be used. Here, B is the translation and A the scale. Now, the scale changes the support of the wavelet based on the scale. So when we change A, we are going to change the frequency by itself. Now, the wavelet must satisfy two conditions: that the average value of the wavelet is equal to 0, and the energy or the square of the absolute value of the base function psi is a value. So it is limited in time, and its energy is countable or is can be defined as a value. Now, scaling in the continuous wavelet transform domain. In the sine wave, as an example, even it's not used for wavelet, however, just to explain the idea, here in the sine, if we have f of t sine t, here we have the scale A. Now we increase the sine scaling by 2. Here A equals 1 over 2, which means 0.5. As you see here, you have now here A is equal to 2, A equals to 0.5, and the frequency is equal to 2. Now, if we increase the frequency or by 4, which means that A is equal to 1 over 4, 0.25, and this will lead to increase the frequency. As here we have compressed time and increase the frequency as we go further by increasing the value of A. So the scale means that you are changing the frequency of the wavelet base function, and this will lead to detect different frequencies in the wavelet domain. Now, in the case of the wavelet, this is for the Fourier, of course, can't be useful for wavelet. In the case of the wavelet transform, I'm going to use different shapes, different wavelets, and by changing this A value, the frequency is changed, and the scale is also is going to change the frequency by changing the scale A. Now, what is the continuous wavelet transform? Actually, is the sum of over all the time of the signal by multiplying the scale by the scaled and shifted versions of the wavelet function. So we have this wavelet function. I'm going to define to change the scales in the integration, and we are going to apply shifting. And the result of the summation or the combination of all these components will give us the continuous wavelet transform. It's a sort of the composition of the signal from the time domain into the frequency domain using a base function, which is called the wavelet, with specific conditions in applying this decomposition or conversion. Now let's do a simple example on the continuous wavelet steps. Let's take a wavelet and compare it to a section of your signal. Suppose that this is your signal in the black color, and this is the wavelet that we take it in this case. And we need now to find what? We need now to find for this specific scale, we need to find the correlation or the let's say the how closely is correlated the wavelet with this section of the signal. So this section of the signal is going to be compared with the wavelet, and we can define the value of C, which is the correlation between this one and this one. Okay. Now for the first step, by having this scale and this with a shift of 0. Next, we can modify by scaling the wavelet by increasing the scale, okay, by reducing the scale, which means that we decrease the frequency. And we can see that the shape here, if we compare to the previous one, you see here 0.01, the C value, the wavelet, and here 0.2247. So the correlation will be higher in this step. And we repeat this for different stages or different A values, and we start to shift until we finish or work with the signal. Now, if we want to apply the discrete wavelet transform into to apply sampling to the wavelet transform, actually, the sampling here will be usually used in the non-uniform domain, or why? Because it's not properly to sample all components in the frequency domain, because the wavelet is a frequency domain. This will give us let's say a sort of now, as if you look at the frequency in the wavelet domain, it looks like that when you have no frequency, you need more samples. When you have high frequency, because the resolution there is not very high, you can reduce the number of samples or the sampling sampler operation by increasing the interval of sampling and reducing the frequency of the sampling process. And this is what we have done actually to use in different wavelets shapes or wavelet functions. One of the good, I don't want to spend a lot of time on this thing. Now we have the Dyadic Grid. As you look here, I can explain using this chart. Now, if you take in the low frequency part, we can take every sample. As we increase the frequency, we take sample yes and on and off, and this process will be repeated and reduced as we go further horizontally or vertically. Here it will be in the scale of log A instead of A, and this is the shifting when we change B and we take the scaling by log A. Here the A value will be used as A naught to the power j, where A naught is a constant value, and while B will be taken as k multiplied by A0 or A naught j by B naught, and again B naught is a constant value. However, what we do is to get the sampling or the discretization to be reduced dynamically as we increase the frequency and change the what we call it the shifting. So let's have a look on some wavelet types used usually in signal processing and other applications. Here we have the Haar wavelets, simple wavelet base function. Okay. Here we have the coifflet. It looks like a sync function more or less. The simlet. We have here the D4 wavelet, Mayer wavelet, and of different degrees, degree 2 and degree 3. Now, what we talk about actually, these wavelets are used as base functions instead of the sinusoidal in the DFT to apply wave transformation by finding the sum of all results by multiplying the wavelet basis function after scaling and shifting all over the time. And this will give us the output wavelet result. Now, what for this actually can be seen in domain in the one-dimensional and two-dimensional domains as the projection of the signal in the frequency domain at different frequency ranges or different frequencies, let's say frequency projections or decompositions. Now, if we take the one-dimensional Fourier transform by having a base function this way, these values for the psi function, related relation between the psi function or the base function at level j, or level, it will be related to the psi at the previous level as you see here. with dyadic decomposition with A equals 2 to the power j and B as 2 multiplied by 2 to the power j. Actually, this is the forward wavelet transform of having this wavelet coefficients multiplied by the signal in the time domain and getting the wavelet transform in one dimension. And the inverse will be applying this operation as having the function psi to get the opposite operation to the time domain. Actually, the wavelets are better explained in the domain of the filter banks by having two filters having two frequencies, one with low frequency and the other one with the high frequency. Let's have a look on this small sketch. Now, suppose that this is the signal in the time domain, and we want to decompose it into the frequency domain. Usually, we take the spectrum simply. This is the max of the frequency in the frequency. And we divide this frequency into two parts, low and high. Then we repeat this process to get low of the low and high of the low. Then we can divide this as other part, etc. And we continue the operation until we reach the desired level of the wavelet transform. Okay. Let's have a look here on this idea. This is the input signal. We have two filters, H1 and H0. These filters are used for analysis. Usually they are low pass filter and high pass filter. Then we apply here, as you see, we can apply the decimation or the downsampling by a factor of 2. Downsampling by a factor of 2 again. We get the intermediate output or the output Y1 and Y0. Then we apply over sampling by a factor of 2. And the same thing here to get the filters, the opposite filters of these ones. Here we have the analysis filters, and here we have the synthesis filters to get. So we have filter H1. Its opposite operation will be G1 in the frequency domain. And after that, we can get X1 in the low frequency part, in the high frequency part, for example, in the high frequency, in the low frequency part as X node, then we combine and get the result. Now, why we use the decimation or downsampling by a factor of 2 and oversampling by a factor of 2? This idea is just to keep the input X and the intermediate here, intermediate outputs or the Y here, if we have this Y1 and Y2 of having half the size of X, and this will give us a possibility not to increase the size of the data after applying discrete wavelet transform. This is in one dimension and one level DCT using filter banks. The main idea here is to use low pass and high pass filters, the complementary, to get this is the transfer function of H node and H1 filters. As you see here, they are the low band and the high band filters having half free sampling frequency pi over 2, and we get in this case the complementary of the two operations. This we call it the filter bank pair, one for the low pass and one for the high pass. Now, to realize this, we can use the simplest wavelet application, which is the Haar filter bank. Here for the low pass filter, we can use H0 n in the time domain as 1 over square root of 2 for the value of n equals 0 and minus 1 and 0 otherwise. Now for H1, we have 1 over square root of 2 for n equals 0, and for 1 or minus 1 over square root of 2 for n equals minus 1 and 0 otherwise. Of course, these two filters are the impulse responses of these filters in time domain that will be converted into low pass and high pass filters in the frequency domain. The length of the filter is just of 2 elements actually, and you can add 0 padding if you are required to have longer sequences. This is just in one dimension. Okay, this is an example on Haar wavelet transform. Suppose that we are asked to find to apply wavelet transform for an image by dividing it into 4x4 blocks. Now we can apply, as you see here, we can apply the Haar transform for an image block of the size 4x4. Now this function is 2x2, 2x1. So we can apply 0 padding. As you see here, we have This is the original low pass, and this is the original high pass in dimension of the Haar of 2 by 2. Now we just need, because we have here 4 by 4 elements, so we need now to do what? We can just apply zero padding to reach the same size of 4 by 4. It's in one dimension. Now, how to apply convolution between the filter itself, between this filter. So this low pass filter will be used with the image segment or a 4 by 4 block by applying to firstly by the row direction, then when we finish by the column direction, to apply in 2 dimensions. Now, how to apply this? Well, where to convolve? For example, if we have an image sequence of, let's say, for example, 120, 30, and 45. Now, how to apply this? We just need to put the origin right here and perform the operation. As here we can read here, this text is given here, that the origin is, note that when the vector is zero padded on the right, the origin is no longer to the right of the center of the resulting vector. What is meant by that? Let's explain with clear. Let's have here a text of red, maybe another color. Suppose that we have the values that want to convolve the image with is 120 or 120, 35, 30, maybe 30, it could be any value, and 40. Now, if we look at the 1, 1 and 1 minus 1 of the Haar. Now, the origin is located at, is placed into the location corresponding to the origin. How we can define the origin? As we can read here and see here, the vector is zero padded to the right. The origin is no longer, and now the origin will be, we take the center. This is the center of this low pass filter, and this is for the high pass filter. This is origin. But now we select the element on the right hand of this center, the midpoint. This is the center of this filter. Now the center will be applied to the element of interest. For example, it could be 140, 20, or maybe 30. Depends on your application. We just apply now the low pass filter to this window, and the high pass filter the same thing, to get the output for the pixel at this location. For example, 180, or I think it's 20. Okay, it's 20, 120. When we go further, for example, we want to find 430, we again put the center on the 30 and the elements in the 4 by 4 dimension in the direction of rows and direction of columns. This way we can get the wavelet transform in 2 dimensions for image of the size 4 by 4. Okay. And this is the transfer function for the Haar. Now, if we want to repeat this for the Daubechies, for example, and here we want to apply operation on 8 by 8 blocks. Now, the Daubechies has 4 by 1 size. We look at the origin. This is the mid point. We locate the origin at the right hand side, at the right to the center, and now we add zero padding. Next, we go for to find for the image. We get for the image its value for a matrix of 1 by 8 for every row, and we put the center, which is this one, on the pixel under consideration, and get the value of this filter output. This is for the synthesis, the analysis, and this is for the synthesis of the Daubechies filter. Okay. Now, in block diagram shape, this is the one-dimensional filter. We get the input image. We divide into low frequency and high frequency components in the row direction and in the columns direction. This will lead to produce 4 subbands. here we have the approximation subband. As you look here, we can follow this line. This will be applied to the low filter in the row direction, and low filter in the vector in the column direction. While this one will be applied in the row direction as low, and it will be applied in the direction of the columns as high. So we can say that this one is low and low, this one is low and high, etc. Can repeat this way to get for all other subbands. So the one level decomposition will give us this for the as you see here, we have low, 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 high, low in low pass in row direction, and high pass in the column direction. And we continue until we finish the 4 subbands. This is for the analysis, and the opposite operation will be for the synthesis to get the original image after transformation. One level is one level wavelet. Usually, we can do this in more than one level. We can repeat this into this one level, as we have seen here. This one level in row and column directions. Now we can take this image or this wavelet part and apply wavelet again to the second level. Usually we take the low frequency part only to apply the second level, and next the third level, fourth level, etc. Why? Because the most important part of the information is concentrated in the low frequency part, and as we go further in a zigzag fashion, the importance of the resolution will be reduced monotonically. Here we can find different demos. This one level wavelet for the image layer, for the color image, these roses, maybe flowers, and here for 2 levels. As you see here, we take the first level. This is the first level. Then we repeat the process by dividing or by the decomposition into 4 subbands. Sorry, and etc. This is for Lena. Here the second level, and the first level for all components. A lot of applications can be found on the Fourier. First of all is the JPEG 2000. It's an extension of the JPEG using, instead of DCT, we use JPEG. Image enhancement techniques, filtration, denoising, all these things can be done. Image watermarking and security applications, etc. You can find a lot of applications with MATLAB things. Now let's go and see. I'll try to show you a MATLAB. Here, if you go to MATLAB and you type wave menu, we'll find a demo in MATLAB. As see here. Okay, let's maximize this one. Okay, let's move my picture somewhere at this place. Okay, now you can see here we have a lot of applications. One-dimensional wavelet, 2-dimensional, we have 3-dimensional, multiple 1D, specialized tools like denoising, estimation, etc. All these things can be found in research papers and in other autoscope works. You can apply extension of images. Now let's go and take, for example, wavelet in 2 dimensions. I like this demo. And we select this one and see what will happen now. Just a moment, it's loading. Now, as you can see here, let's go to this place because we now file. Let's select load a given image, for example, an image. let's say grayscale open. Just a little bit, it takes some time because you see that this is the original image. Now we want to apply the wavelet decomposition for the analysis. I'll try to minimize my picture here, my video. Okay. Now we can select the wavelet type, base function. We can have Daubechies, Haar, Simlet, Wavelet, etc. Let's talk about Haar, for example, and take two levels, or let's take one level, and apply analyze. We'll see what will happen now. And so here we have got the forward, the discrete wavelet transform, and this is the inverse. And we have here the one level wavelet transform. If you look at this one, okay, or this one, or this one, or this one, you can select now. I think that we have some problem here. However, we can now find some statistical analysis, statistics for every subband in the wavelet. We can have a lot of information regarding these images using this part. You can see that the mean value, the median, the maximum, the minimum, standard deviation, etc. All these things can be found in using this tool or toolbox or example. Now let's apply two-dimensional and see what will happen. Analyze. It's clear that we have two-dimensional wavelet. Okay. Let's select this one, for example, this one or this one. Okay. This full size for the first direction, the first subband, second subband, fourth and fifth subband, fourth subband. Here the subbands are clearly seen on the screen for the first level and the second level wavelet. Now we can repeat this for more levels. Sometimes we may approach 5 levels if you want. Let's close this one and go 2D dimension. Again, here we take another image, for example, let's take two color images like مثلا jellyfish. It's an image built in MATLAB. And we can do now 4 levels. Let's take now, I see 3 levels because analyze and see the results. I see that most of the details are found in the lower part of the frequency, and as we increase the frequency to the in the other subbands, we can see that little details are found. This actually can be compressed, and as a result can be removed from the wavelet domain and apply compression in this way. Hope it was enjoyable for you, and see you in next slides inshallah or next lectures. Assalamu alaikum.